Welcome to the lesson 23 of industrial instrumentation. In this lesson, we will continue with the signal conditioning circuit. So, this is a signal conditioning circuit 2. In lesson 22, we have discussed some signal conditioning circuits. We have discussed the filters, and basically we concentrate on the single amplifier filter. But as you know that filter is one of the most vital part for analog signal processing. So, we have devoted at least 1.5 lessons for filters. Now, these analog filters are off the shelf devices. I mean, you can make the filters with a very low cost, and it will give you good performance also if you can design it properly. Now, the single amplifier filter suffers from the drawback that the tuning of the filters is very difficult. As you know, the filters has some typical parameters. This is omega p, q, p and k, which we have discussed in the lesson 22 in details. This basically depends on some resistance and capacitance, right. Now, in the case of filters, whatever you will design, whatever the filters you will design, obviously you know that due to imperfections of the components, I mean, if you say that your design components, I mean, actual design equation gives you a component value of 923 ohm. So, instead of 923 ohm, it is very difficult to get that value. You may get it is a little deviate. Even if you get that exact value, there will be some tolerances of that resistance, which will lead you to ultimately, once you design the circuit, some sort of tuning of the these filter parameters omega p, q, p, k, omega z, q, z. Now, the problem of the single amplifier structure is that it is a low cost. Its signal dynamic range is also good. Its signal to noise ratio is also good. Unfortunately, if your technology does not permit very tight component tolerances, so the tuning of the filter parameters is very difficult in this case of filters. And in this lesson 23, we actually discussed these two amplifiers and the general impedance converters, two amplifier based general impedance converters, then two amplifier based filters and state variable filters, and then sample and hold circuit, and then logarithmic and anti-logarithmic amplifier. These all is a very common sort of circuits which is frequently used in signal processing or signal conditionings. Let us now lesson 23. You see the contents of these lessons are two amplifier filters, a general impedance converter, okay, and state variable filter. Then we have sample and hold circuit. We will also now let us look at the general impedance converter. You see the general impedance converter, the circuit looks like this. Okay, you can see here that in case suppose I am interested to measure the output the input impedance of the circuit. So, okay, from this point, what is the input impedance circuit? So, I assume that this voltage is V, and obviously we can see here that that this resistance, this is connected to ground, and this general impedance converter is basically a device or circuit which will give you the you can simulate inductance from the capacitance. As you know that it is very difficult to implement the inductance in integrated circuits. So, people tried over the years to simulate this inductance with the help of capacitance. Now, the general impedance converter, you can simulate inductance with the help of a capacitance. You can simulate capacitance with the help of inductance, but nobody actually simulate capacitance with the help of inductance, because that is not necessary. In integrated circuits, we can always fabricate capacitance of the wide values or widely different values in the chip itself, which is not possible in the case of if I want to do it the inductor in the chip, even though people tried for last 2-3 years to make a on chip inductance, but it is still in the research state, right. Now, you see that I want to measure the input impedance, or I want to look at the input impedance of the circuit looking from this terminal, right. So, that in this connector I connected a voltage source V, and I measure the current which is going inside, right. So, you see two op amps are connected. So, that is the reason we call two amplifier structures, and let us make the analysis of these circuits. We will apply the Kirchhoff's voltage. Now, one thing is very common, you see, this op amp has very high input impedance, right. So, this potential at the node 1 and potential at the node 3 is same. Again, since this op amp, this potential 3, you see node 3 is common, here, you see here. So, this is connected again the second amplifier. So, this potential node 3 potential and node 5 potential is same, clear. So, if I now apply the Kirchhoff's voltage law in the node 5, we will get, we apply the Kirchhoff for the circuit analysis, applying the KCL's, Kirchhoff's current law, I will get V2 minus V SC equal to V by R4. Now, let us look at what is, okay. So, this is our V2, you see here, this is our V2. So, this is our V2, this is our V1, okay. Now, I want to apply this in this loop, this our Kirchhoff's current law. Let us look at what we will get. Yes. So, applying Kirchhoff's current law also at the node 3, we will get V1 minus V by R2, V minus V2 R3. So, or V minus V1 by R2 equal to V2 minus V by R3. So, if this is the equation, so obviously substituting V2 minus by V from equation 1, we get V1 minus V1 by R2 equal to V by S R3 R4 C, right. So, applying KCL at node 1, I can write I in, that means current which is flowing inside just at the input node, V minus V1 by R1 equal to V R2 by S R4 R3 R1 C. So, obviously, so V by I in or the input impedance of the circuit will look like S R4 R3 R1 C by R2, right. So, Z impedance, so I can write Z in is equal to the input impedance of the circuit at the node 1 can be written as S R4 R3 R1 C by R2. Now, you see this entire things I can write as an equivalent inductance, you see this entire thing, is not it. Okay, so, I can write it as LEQ. So, we can see interestingly using one single capacitors I can simulate inductance in the circuits. So, I have used one capacitors and some resistors. So, I am simulating actually the inductance in the circuits, right. So, it is a tremendous impact in the signal processing in instrumentation at least. So, thus I can write the L equivalent or inductance equivalent equal to R4 R3 R1 C by R2. You see there is a various combinations of this, you can have any one of this one, suppose you can choose R4 also, okay, as in capacitance by which you can get the equivalent inductance, right. Now, thus the above two amplifier structure simulates an inductance, that is actual. Now, you see one thing is very important, if you look at these circuits, you see this particular circuit will generate actually the grounded inductance. Now, if I want to simulate the floating inductance, then these two circuits should be connected back to back, right. Only that time you will get the inductance, the floating inductance. So, now the inductance which we have generated here is a grounded inductance. Now, with the help of this inductance, I can obviously simulate low pass, high pass, band pass filters can be realized using these two amplifier structures. I can realize low pass structures, I can realize high pass structure, I can realize band pass filters using the two amplifier structures. Now, you see if you compare these single amplifier structures and two amplifier structure, you won't get much advantage in these two cases, except in the form that that you will find that in the case if you use a band pass filter, it will give very high input impedance at resonance, okay, which we will not get in a single amplifier structure. Otherwise, all the problems what you have in the case of single amplifier structure, that means the tuning difficulty, which is most obvious in this case also, will remain there. So, I am not getting an advantage compared to the single amplifier structure so far the tuning of the filter is concerned, right. Now, low pass filter, let us look at these low pass structures, that means between input between this input and this input output, I will get a low pass structure. That means VO by V in will give you a value like K divided by S square omega p by QP S plus omega p square. This type of structures it will get, right. Now, if I want try to analyze these circuits, for circuit analysis I can find out that the V naught by V in S 1 by 1 upon R1 R2 multiplied by 1 upon R4 plus 1 upon R5 multiplied by R5 C1 C2 and upon S square plus S by R3 C2 plus R5 R1 R2 R4 C1 C2. Clear? Now, see that I mean if I can similar as it happened in the case of general emitters, I mean making the circuit analysis for the general emitters converter, that same thing we can do it here also to find the overall I mean transfer functions in S domain of the circuit, right. Now, also I can write the nodal admittance matrix of these networks and find the transfer functions. I am not going to details of that. Now, let us go back again. So, this is my circuit. So, it is a very equivalent, I mean I can obviously this I can write what I can write at this I can write k equal to as I just written S square plus omega p by q p S plus omega p square, is not it. So, this will give you omega p square. So, square root of this will give you the square root of this will give you omega p. See, if I make the square root of this I will get the omega p and this will give you omega p by q p, right, and this will give you capital K. So, obviously, as you can see also here it is very difficult. You see the R3 is present, obviously you can choose R3 to tune the QP. So, not that difficult, you can choose R3 to tune QP, but in tuning the K, that means gain constant, is also difficult there, because you see whatever there R1, R2, R4, R5 everything is present here. It is very difficult to tune omega p and capital K independently, though I can tune QP and omega p independently in this particular type of circuits, right. So, design equations are R1, R2, R4, R5 equal to R I have taken, R3 equal to we have taken QP and C1, C2 all equal, C you can take 1 farad accordingly resistance will come and C multiplied by R equal to 1 by omega p. So, omega p equal to 1 by CR. Now, you see the high pass filter slightly structured, the basic 2 amplifier structure remains same, we are making little modification. You see this is basic 2 amplifier structure remains same. Again I am giving the input here, I am taking the output from this position, right. You see the 2 amplifier structures, I am giving the input here, I am taking the output here, see here. So, as it happens in the case of general impedance converter, in these cases also I can take the transfer, I can find the transfer function between an input and output, and I can find the transfer functions as well as I can find the design equations for this type of high pass filters, right. You see from circuit analysis obviously I can write S square into 1 plus R4 by R5, S square plus S upon R1 C1 plus R4 upon R2 R3 R5 C1 C2. Now, design equations are R1 equal to QPR, R2 R3 R4 R5 equal to R, C1 C2 equal to C and CR equal to 1 by omega p, right. Now, band pass cases you see here that R1 similar structures, only there is some difference at the input side. Again I am giving the input here at this positions, I am taking the output from this position. You see I am giving the input in this position and taking the output from this position, input at this position, output at this position, fine. So, again I am finding the transfer function V naught upon V in S domain. So, I will get a transfer function which looks like this. So, obviously it is a, you can see here there is a single 0 at the origin and 2 complex conjugate poles. So, V naught by V in S equal to S 1 plus R4 by R5 upon C1 R1, S square upon S square plus S upon R1 C1 plus R4 C1 C2 R2 R3 R5, right. And the design equations looks like this: R1 equal to QPR, R2 R3 R4 R5 equal to R, C1 equal to C2 equal to C and CR equal to 1 by omega p. Now, state variable feed forward structure looks like this. Now, you see we have discussed about the second amplifier structure using 2 amplifier. I have just discussed it only low pass, band pass, high pass, but you can use, you can simulate, you can generate other, I mean you can make the other topology like the high pass notch, low pass notch or band reject or all pass also with the single amplifier structures, right. I am not going to details of that, so I am just giving the two amplifier structure where we can make low pass, high pass, band pass. Please remember you can generate other filter functions like high pass notch, band pass notch, band reject as well as all pass structure by this two amplifier topology. Now, as it happened, as I told you that in the case of single amplifier structure, it is just impossible to tune orthogonally all the filter parameters. In the case of two amplifier structures, we have seen that we can independently tune the omega p and QP quite obviously, but I cannot tune QP, omega p and K independently. So, people need some other structure where we can make total orthogonal tuning of the filters, right. So, that type of structure is basically state variable feed forward structure. Let us look at the 3 amplifier structure. Looks, you see that we need 3 amplifiers. Why it is calling feed forward? You see there is a feedback, there is no doubt the state variable structure. Okay, I have a lossy integrator. You see what is this actually? So this is a lossy integrator, right? This is an inverter, simple inverter, and this is another integrator, is not it? So, the first one is the lossy integrator or damped integrator, then you have an inverter, then we have again another integrator. And we see here there are feed forward through R6 and R7 because input is coming here, it is going to R4 to the first amplifier, then through R6, you see through R6 and through R5 we are giving 2 feed forward. This type of structure can generate any filter functions. Okay, we will see that's the advantage of this type of structure, tremendous advantage of this type of structure. It is available in the cheap form also. This type of filters, National Semiconductor makes this filters is called universal filter, where you can have one or two elements outside which you can tune to get your desired value of omega p and QP, right. Now, design equation looks like this. From the circuit analysis we can make the circuit analysis. We can say that R8 minus R8 by R6 S square plus S 1 by R1 C1 1 by R4 C1 R6 R7 R6 by R7 1 upon R3 R4 C1 C2 S square plus S 1 upon R1 C1 R8 by R7 1 upon R2 R3 C1 C2, right. One thing you see here which is very important, you see here that this is very similar to the structure. I can write Ts equal to minus K S square Cs plus D S square plus As plus B, is not it? Very similar to this type of structure. Now, for this reason you can see this all this value R8 these components, you can see this component, this one. So, we can realize by some resistance and capacitances. So, if I purposefully make that portion 0, obviously I can get it. Suppose in this case, suppose if I make C 0 and D 0, so it will be high pass structure, right. Similarly, if I make suppose R6 infinite, in that case it will be I can make this as a low pass or band pass structure, like that it goes, right. So, with this type of structures obviously I can generate any filter function. Only problem, if you look at the numerator, you see that here we have a subtractive term at the as a coefficient of S. So, the problem with this subtractive term is that we have to make the signal, we are making it 0, this coefficient is 0 by signal subtractions, right. So, in that type of situation what will happen, if there is suppose in that case if this pole zero cancellation is, if this coefficient is not exactly 0, this coefficient is not exactly 0, then what will this coefficient is not exactly 0, then we will find that even though I try to realize the low pass structure, so in the case of low pass structure, as you know, the pole zero pattern will be like this one, so 2 complex conjugate poles are no zeros, so it will find that it will not exactly the same pole zero pattern, right. So, these only difficulties in this type of state variable structure, otherwise it is a tremendous advantage. Its sensitivity is also quite low, its tuning is a great advantage. You can see in the next slide I can show you what are the different elements we can choose to tune omega p, QP, omega z, QZ independently, right. Because as you know in that in the filter parameters we know that we have to tune omega p. You can take another pen. omega p, qp, capital K, omega z and qz. These are the things which we are going to simulate, right. So, these are the parameters which you have to tune it with some resistance elements. Capacitance we will not use for tuning. Now, how I can make now orthogonal tuning means that if I use some resistance to tune or some capacitance, I will consider the resistance. If I consider some resistance, suppose this omega p I want to change or modify or tune. So, other by changing some resistance, if I tune omega p, other filter parameters should remain intact. That is called the orthogonal tuning. Okay. Now, if you go back, you see here, what will happen in this case, I can choose some of the resistance. Suppose if I choose some of the resistance to tune omega p. By that time, what will happen? You see that if I choose some resistance to tune omega p, there is omega p. What will happen? That omega z, qz may change. It does not matter. Let it go wherever it goes. Then we will use some other resistance or capacitance to bring it back to the original position, right. So, let us look at that. Now, above equations, as you can also be written as Ts equal to K S square plus Cs plus D S square plus As plus B, and the design equations are C1 C2 equal to 1, R2 R3 R7 R8 equal to R equal to 1 by root B, and R1 equal to 1 by A, R4 equal to 1 upon K A minus C, R5 equal to root over B by KD, and R6 equal to 1 upon K root B. The design equations mentioned above yield positive element values for A greater than C. This most of the cases this will be satisfied, A will be greater than C. These design equations mentioned above yield positive element values for A greater than C. And the above equations can also be written as Tk, Ts equal to K S square plus omega z by Qzs plus omega z square upon S square omega p Qps plus omega p square. And thus for orthogonal tuning we can use the following elements as shown in the table below, and they need to be done sequentially as given. Okay, you cannot haphazard fashions. These are the filter parameters and which particular element, passive elements you will choose to tune it. Let us look at, for capital K gain constants I am tuning R8, right. For omega z I am using R3. For omega p I am choosing R2. Omega p qp equal to R1, I am choosing R1 to tune, and qz equal to R4. This completes the tuning of all the filter elements. You have to go in particular this sequence, that otherwise there will be a problem, you see, because if you choose tune R8, let us look at, I am taking examples of tuning R8 or R3, omega z k for R8 and omega z equal to R3. Let us look at. Now, you see here, so K we are using R8 and omega z R3. Let us look at, you see that K to R8 is changing. Okay, I am getting the proper value of R8 by tuning this proper value of capital K. This is because this K is equal to R8 by R6, is not it? So, I am tuning R8 to getting proper value of K, but you look at that R8 is also present in the expressions of omega p. So, omega p will change, right, it does not matter, let it change. Okay. So, I will bring it back by using some other elements to its desired value. Similarly, you see that when I am after K, once the K is tuned, now I am choosing R3 to tune omega z. What is omega z here? You see it is omega z. Now, this also will vary by during that time, it does not matter. I will choose some other elements later on. So, to tune get the omega p exact desired value. So, this sequence, that is the reason I am telling that particular sequence you have to maintain, otherwise there will be a problem. Now, you see, so once I have chosen R3 to tune omega z, I am not using R3 anywhere to choose any other further elements. I will choose some other elements to tune the omega p or qp like that, right. So, that is the case that I want to explain to you. You see is here, sorry, here you see omega z R3, omega p R2, q p R1. So, if I vary omega z, then what will happen? You see, if I vary R3, omega p will vary, does not matter, I will use R2 to bring it back to the original value, right, or desired value. Similarly, I can tune qp and qz by R1 and R4 respectively, right. This ends the particular the only the filters, that means we have discussed in the lesson 22 the single amplifier structures, then in the lesson 23 we have discussed the 2 amplifier structures, we have discussed the 3 amplifier state variable structures. State variable structures has another advantage, its is the frequency, its sensitivities, logarithmic sensitivity is very low. Though the one single problem with the single amplifier structure is the power dissipation and also the dynamic range of the filter, because as you know, if you are increasing the number of op amps, you are making your signal to noise ratio poorer and poorer, right. But I mean since it has the advantage of the tuning and it has the advantage of the low sensitivity, these structures is preferred over the other single amplifier or 2 amplifier structures. Now, let us go back to sample and hold circuits. Let us look at that. You see, this is a simple sample and hold circuits. In sample and hold circuits, very much necessary in many signal conditions. One of the good example of the sample and hold circuit is ADC. Now, analog to digital converters, we have, you know, there are various types of analog to digital converters. We have successive approximations analog to digital control. We have a counter control ADC, we have a dual slope ADC, we have a flash ADC. There are so many ADCs are there, enhanced dual slope ADC. Now, all these cases, I assume that during the conversion, whatever small it may be, all the ADC has some conversion time. We are assuming that during the conversion, the signal remains stationary of value. This value is not changing. That's to be assured by the sample and hold circuits, right? So, sample and this is one of the simplest form of the schematic of the sample and hold circuit. This is a switch and we have a capacitors here. Okay, when I close the switch, it is charged, the capacitor is charged by the input voltage, and when I open it, it will hold for that for some period, right, whatever small it may be. So, during that times I can make my conversion studies, my conversion complete. Let us look at, sorry. Now, voltage across the capacitor tracks the input signal during the time Tg when the logic control gate S is closed. This is a logic control gate. I can use some MOS gates also, right, for this purpose. The capacitor holds the instantaneous value attained at the end of the interval Tg when the current gate opens S, right, fine. So, during Tg, so it holds the charge. The switch may be a bipolar transistors or a MOSFET controlled by V gating the signal voltage or a CMOS transmission gates. Now, you see these are examples. So, I am using MOS gates. Here I am using one buffer amplifier at the input side, another buffer amplifier at the output side, right. So, this gets these analog signals. So, whenever this gate voltage, if it is NPN, suppose if it is an MOSFETs, MOSFETs, if it is, the signal is like this, what will happen? So, whenever this voltage is positive, it is open. So, whatever the charge it has voltage, it will be come to this and capacitor will be charged to that voltage. Okay. Once this gate voltage is removed, so that voltage is supposed to stay here. So, during that time, if the V1 changes, that will not affect this output voltage or the voltage on the capacitor C. Okay. That is the basic theory of the sample and hold circuit. Now, positive pulse at the gate of NMOS, if I assume it is NMOS, so in the gate I have to give positive pulse, positive signals or control voltage. If I use a PMOS, I have to give negative voltage or negative signal at the gate of the NMOS or of the PMOS. The holding capacitor C will charge to the instantaneous value of the input voltage with a time constant of R0 plus RDS on multiplied by C. You know, the time constants means basically R into C. So, where R0 very small, output resistance of the input op amp A1. Okay. Assume that the output, obviously this op amp has a very low output impedance. Now, RDS on is the on resistance of the MOSFET. I am writing FET is the MOSFET, on resistance of the MOSFET, right. In the absence of the positive pulses, the switch is turned off and the capacitor is isolated from any load through the op amp A2 and thus will hold the voltage impressed on it. Okay. So, because there is an output capacitor, so obviously it will isolate our output circuits this sample and hold circuit will be totally isolated from the subsequent circuits which follows after the amplifier A2, right. So, this charge will be hold because there is no path to discharge. So, that path charge should hold if there is no leakage in the obviously in the capacitor. So, the capacitor is the crux or the heart of this sample and hold circuits. We will discuss what are the different types of capacitors typically used for making a sample and hold circuits. It is recommended in discrete component or hybrid circuits a capacitor with a polycarbonate, polyethylene, polystyrene, mylar or Teflon dielectrics be used, because all this name actually came for the capacitors for the typical dielectrics. This is dielectrics which is used for the which is placed inside the plates of a parallel plate capacitors. So, we are talking of the not necessarily it will be parallel plate, it can be foil type also, as it happens in the case of electrolytic capacitors. In most other capacitor than mentioned above, there arises two major problems. They are polarization phenomena which causes the time constant to decay with the time constant of the several seconds. In effect, this is the leakage resistance of the capacitor. Dielectric absorption which causes a capacitor to remember a fraction of its previous charge, that is also create the problem. Even if the polarizations and the absorption do not occur, the off current or the current of the switches is less than 1 microampere, less than and the bias current of the op amp will flow to the capacitor C, right. That is the problem. Since maximum input voltage, input bias current is less than 1 microampere, it follows that with the capacitor 0.5 microfarad, the drift rate during the whole period will be less than 2 millivolt per second. There are two additional factors which influence the operation of the circuit. They are the aperture time, typically less than 100 microsecond, which is delay between the time when the pulse is applied to the switch and the actual time the switch closes. Aperture time typically less than 100 microsecond, which is the delay between the time when the pulse is applied to the switch and the actual time the switch closes. Acquisition time, which is a time that the capacitor takes to change from one level to holding voltage to the new value of the input voltage after the switch is closed, is not it. Because you see what will happen, that the capacitor, suppose I have some voltage, okay, I have some voltage on the capacitors. So, if you charge it, suppose its voltage is changing, so it will from this place for during that it is remains constant. So, it will go again to that value, okay. We are talking about that. Acquisition time, which is the time that the capacitor takes to change from one level of holding voltage to the new value of the input voltage after the switch is closed. Now, next we will discuss the logarithmic amplifier. Logarithmic amplifier is basically an amplifier which will give the signal the output, this one. So, the output should be some constant multiplied by logarithmic of the voltage Vs, okay, that is the function of the logarithmic amplifier, right. So, the output is a logarithmic of the voltage Vs. This is the basic principle of logarithm amplifiers. We can use the two transistors and two amplifiers to make the logarithmic amplifier. The circuit analysis shows that is basically use these the diode characteristics of the, because you know diode characteristics is exponential characteristics of the voltage current relations of the diodes. That principle is utilized to make these logarithmic amplifiers. If I make the circuit analysis, you see here, assuming that IB1 is much less than IC1, that is quite obvious in all the cases of the transistors, and in the transistor 2 also IB2 base current is much less than the collector current. In the transistor 1 the base current is much less than collector current. In base 2, in the transistor 2 base current is much less than collector current. We get V0 equal to minus Vt R3 plus R4 by R3, natural log of Vs by R1 into R2 by Vr. So, obviously you can see that if I assume this R1, R2, V are all constant, so only variable here is the Vs, because Vt is also constant for a particular room temperature, this Vt will also remain constant. So, you can see that V0, and if I assume this R1, R2, Vr reference voltage all are constant. So, this output voltage is a logarithmic of the voltage Vs which we have impressed, right, which is applied at the input of the circuit. So, this is basically the logarithmic amplifier. Similarly, since we have a logarithmic amplifier, we can have an anti-logarithmic amplifier also. Well, let us look at In anti-logarithmic amplifier circuit looks like this, is basically same. You can see 2 transistors and 2 amplifiers, A1 and A2, and 2 resistors R4 and R3 at the initial site. So Vs output will be anti-logarithmic of the voltage which you are giving here. So let us, if we make the circuit analysis, I can write that V naught equal to R1 into Vr by R2 exponential of minus Vs Vt into R3 plus R4, right. So you can see this one, this is a negative logarithmic of the, so this is obviously this, you can see this is anti-logarithmic amplifier. Analog switches is extremely used in signal conditioning circuits. The analog switches are the 2 switches, one NMOS and one PMOS. I think this figures I have to modify, actually it looks like this, and this is NMOS, this is PMOS, or I can use a symbol like this as it happened in the case. This is NMOS, and in the case of PMOS there is no arrow, or you can be like this one, right. This is in the case of PMOS. I am not showing the substrate, so okay, or bulk. And now if you look at this NMOS, PMOS, these all basically called a CMOS switch. It is extensively used in the signal conditioning circuitry, in the multiplexing, in demultiplexing. Now what is this PMOS? Why should I use 2 MOS in parallel? Because if I have to give plus Vg here, I have to give minus Vg here to turn on these 2 transistors. There are some advantages. You see, this is a complementary MOSFET switch or CMOS switch, a combination of PMOS and NMOS in parallel, right. Now on resistance of the MOS is a nonlinear function of the voltage drop across FET. That means Vi minus V0, so the nonlinear function of the phase. So this can be linearized by using, in one case it is increasing with the voltage, in another case it is decreasing with the voltage. If I use 2 MOS op amp in parallel, so this will be nullified and the voltage relations, voltage and our turn on resistance relations will be perfectly linear, or it will remain, it should remain constant. So as Vi increases, resistance of T1 increases and that of the T2 decreases. Thus the on resistance of the CMOS is linear and is independent of Vi and is valid for both Vi positive and Vi negative, right. Now this is a symbol of analog switch. You can see this is a bidirectional analog switch. We have Vi, we have Vo, and we have the control signals. This, when this signal is on, that means the signal MOSFET is turned on. So whatever the signal, analog signal that will appear at the output, this is, please note this is not an inverter switch or anything, it is an analog switch. So whatever the signal voltage here, what is the level of the voltage, it does not matter. If this signal is on, that signal will appear at the output. If you remove this signal Vc, okay, so whatever the signal does not matter, that will not appear at the output of the analog switches. Now using these analog switches, I can use a multiplexer and demultiplexing. Let us look at that. Names of the, there are some commercial excuse me, there are some commercial analog switches. These are National Semiconductor switches 4016, 4066. These are all quad switches, and I mean 4 switches in one chip, right. And from Motorola we have Corporation 14066. This is also the quad switches, and that means one for, so it should be, it is a 14-pin DIP, in both the cases 14-pin dual inline package, right. In one case we will find that in each cases we will find there are 3 pins is necessary, one for input, another for output, one for control. So 12 switches gone, so 2 more switches, one for VSS, another for VDD. So it is 14-pin DIP which holds the 4 analog switches, right. So both the National Semiconductor Motorola specifications we have given. It is a bidirectional analog switch, 14-pin DIP. There are 4 switches on one switch. These are all the specifications. One VDD, one VSS line. On resistance of the chip of analog, I mean switch is around 100 ohm to 600 ohm. Its value is little low. I mean you can keep nowadays it's even less. So input signal lie between VDD and VSS, where VDD plus volt and VSS might be minus 5 volt. And now you see this is one of the typical example of the multiplexing and demultiplexing. Now you see what is the need of multiplexing and demultiplexing. Now basically this multiplexing, demultiplexing is necessary to reduce the number of cables and also the number of hardwares. Okay. Now all of you know, most of you are using the calculators. Okay, in the calculators we have nowadays, as we can afford, you can have a 10-digit display, you can have a 12-digit display, all those things. Now it will be surprising to know, you know, always from if you have a BCD signals, you have to convert to the, I mean, display. So I needed to BCD to 7-segment decoder. Now my BCD signal, BCD chip should be the same as the display unit, but I can use a single decoder, BCD to 7-segment decoder, to convert this signal to the 7-segment display. This can be very convenient to do if you can scan the signals, if you can multiplex. Okay, and due to persistence of visions, if you look at the calculator, we never seen that it's not blinking, it's not due to persistence of vision, it appears that it is constant. Okay, it's not flickering, actually it is flickering. That means 1 digit at a time they are displaying on the display board, right. Similarly, in the case of, suppose in the case of ADC, we have also multiplexing, demultiplexing. One of the good examples of this type of ADC is 0809. Okay, in 0809 ADC you will find it is a basically 8-bit ADC. Now it has an input, I can connect 8 different input to this ADC, even though ADC is only one ADC is inside the chip, but I can take the signals from 8 different sensors. I can, from 8 different thermocouples or 8 different RTD, I can take the signals, because it is multiplexing that signals one at a time, and every time it is only one A to D converter converting the signals. Similarly, I need one demultiplexer at the output also. All these things is necessary to reduce the number of cables. This is very important because the cable cost is a lot, because especially if you use a low capacitance cable, where the capacitive loss is less, you will find that it is very expensive, right. So to avoid that, I always used multiplexing and demultiplexing. Let us look at that. You see here, this is basically analog switches. 4 analog switches are there. You can see here. I have analog switches. These are all analog switch. You can see these are analog, bidirectional analog. So inputs are coming V1, V2, V3, V4, and we have a control signals 1. These are all control signals which is going here, right? And we have a buffer amplifier at the input. We have buffer amplifier. We have drawn a broken lines, and the lines might be very long. Okay, it is the data lines. And you see what we are doing here. I need a 2 to 4 line decoders. What is the 2 to 4 line decoders? Only one line will be selected at a time. When this line, this switch will be selected, all other switch will be deactivated during that time. This is not very difficult. You can see I can have this type of signals. I can have signals like this. You see here. So this is the switch, this is V1, for V1 I should say, or control V1, this is control V2, control V3, control V4. You see when this is on, only when this is high, only the switch 1, analog switch 1 will be selected, all other will be deactivated, right. So if you have a shift like this one, quite obviously I can achieve this type of signals. What is that? You see that when I am giving V1 control signal to V1, which I have shown just right now, so all the signal, even though signals are present at the input, that will not come to the output, because you see all the outputs are connected together, all the outputs are connected. So it is supposed that whenever this signal is on, when this switch is on, all other switch will be deactivated. That means the signal will not come. So it will come through this network cities. Again, it is demultiplex at the outputs. So V1 will appear as V1 dash, V2 will appear as V2 dash. So I am sort of sampling I am doing here. Similarly, when V2 will be on, what will happen? You see this will be deactivated. So this is connected at the input of the op amp like this one. So we have 2 to 4 line decoder here. You see we have 2 to 4 line decoder. So what is the function of 2 to 4 line decoder? So we have 2-bit signals. Okay, because in the 2-bit signals, what are the different states? I can have, I can have 0 1, 0 0, I can take this one, I can have 0 0, 0 1, 1 0, sorry, I have 0 0, 0 1, 1 0, 1 1. These are signals of 2 to 4 line decoders, okay, because mod 4 counter have 4 different states, okay. Since I have 4 lines, I need mod 4 counter. So after 1 1 again it will go to 0 0, when 0 0 will be activated. So 2 to 4 line decoder is very simple, I can do it with the AND gate. So this gate will be selected, so when all other gates will be deactivated. When this is on, so this will be off, right, and when this is, when 0 1 will be there, so V2 will be, this signal will be selected. When 1 0 will be there, this signal will be selected. When 1 1 will be there, this signal will be selected, right. Same signal should go to the output also, right. So this is the basically 2 to 4 line decoder. Now one question immediately arises, then what is the use of this type of circuits? You see that if I don't use any multiplexing, demultiplexing, what will happen? I have a 4 signals, okay, V1, V2, V3, V4, that will be transmitted. So 4 lines I need, but I need a lot of hardware. You see the, so what actually I did? I achieved that I have saved only 1 line. In addition, I need so many counters, decoders, all those things, right. So counter is necessary, decoder is necessary. Okay, I can manage with 1 decoder, that's fine. I can just with from the output of the decoder to go to the both the input and output, that's not a problem, right. Now the question, where is saving? Saving will be there if the number of lines are more. Okay, if suppose if I have 12 lines, I have 12 different sensors. In that case, how many lines is necessary? If I have 12 different sensors, I need 4 lines, okay, for this one, and 1 line, so 5 lines. So I am saving 7 lines in that case, 7 cables I am in that case. So that is the advantage of the multiplexing and demultiplexing, right. So people always, but you know that we have to be 1 to 1 synchronization should be there. That means when these lines will be selected, so simultaneous this line also should be selected during that. It is not very difficult because same pulse, same mod 4 counter output is coming to the both the decoder. So when this will be selected, this will be selected. And at that time all these 3 analog switch will be deactivated, this analog switches also will be deactivated. When this switch is selected, this switch also will be selected, like that it will go, right. So in the circuitry discussed above, much of the cables can be saved in the as the number of switches increases. Now you see that I am giving some input signal V1 of different varieties of the signal V1, V2, which is very slowly varying with time, increasing with time, which is not varying with time. Now if I sample this and some signal V3 which is coming down and V4 is also less value, it is constant. So if the signal looks like this one, what is the sampled signal? Sampled signal should look like this one, okay. This signal will not change, okay. Now this signals are this is coming like this is coming like this. Now what will happen actually? You see that if I pass this signal, how will it retrieve the original? My original signal does not look like this, is not it? How does my original signal look like? Okay, my original signal look like this. Original signal look like this. So this signal, that means V1s, V2s, V3s, V4s should pass through a low pass filter. If I pass this signal to a low pass filter, so obviously what will happen, this all these things will go out, actually I will get a good output which is very close to the input signals. So I can use a simple RC filters also at the RC low pass filter at the output of the multiplexers. That means at this point. You see here I can use some output signals, I can use some capacitors also, so which will reduce that high frequency component. So I will get a signals which is very similar to the input signals which I have given here, V1, V2, V3, V4, clear. So this is the advantage of our multiplexing and you see here. So if I pass this signal through a low pass filter, obviously I will get the original signal. Now on passing this through a low pass filters, we will set back the original signals, okay, that is quite obvious that I can get the original signal. So obviously you can see the same type of hardware is also used in the case of display, digital displays, where we are saving the 7 segment decoder, because that is a great saving, even though those are in LSI, large scale integration So the saving is there that with a single decoder I can, and due to persistence vision here also, so in many cases I don't need sampling that fast, right. I don't have to monitor the temperature. Suppose I have a 100 thermocouples, I don't need to monitor the thermocouple temperature every minute, something like that. I can sample, suppose if I once in a 5 minutes, that's more than enough. So in that case accordingly I can make the circuit so that which will give you I can sample the circuit like that. So this is the advantage that in that case what I will do, that I will save the basically the hardware which is necessary to I save the hardware which is necessary, which is great, which will reduce the cost of the entire systems or entire equipment. So that is the advantage of the multiplexing and demultiplexing. And in the case of filters, which you have seen, that at the very beginning of the lessons we have discussed, you see the basically general limited converter or inductance simulator. Sometimes it is called the inductance simulators. There are various types of name. We call inductance simulators or gyrators. That means by using a capacitance I can use the inductance, by using an inductance I can use a capacitance. As I told you, nobody simulate nobody simulate the capacitance with the help of inductance, but it is quite obvious people always try to simulate inductance with the help of capacitance, because having a real inductance in a circuit is very difficult. It's not that it is possible so far as for today to get a large value of the inductance. And also we can have a, if we want to do the simulation, I can have a floating inductance as well as we have a grounded inductance. That means two grounded inductance, if we connect back to back, I will get a floating inductance of the simulator, floating inductance circuits. So these are the things which we have discussed. We have also discussed the single amplifier structures, which in the lesson 22 we have discussed the two amplifier structures in the lesson, and we have discussed also the two amplifiers as well as three amplifier state variable. Now state variable structure is a very attractive. Two amplifier structure has no additional advantage, except that in the band pass cases it gives the very high input impedance. Only problem with the state variable structures, we have seen that because you see that the high pass structures, high pass notch or low pass notch, this type of filter functions is achieved by making the coefficients of S in the numerator 0, and we have seen that is actually done by the signal subtractions. So due to the mismatching of any resistance or capacitance, if it does not make 0, that creates the problem. That means in the case of, as you know, in the case of notch circuits, as you know, that we have always, what will happen, that if you look at, this is sigma j omega plane, okay, we have a complex conjugate poles in the case, and either I can have a 0 here, or I can have a 0 here, here, or here, here. Now if it does not cancels, that means that there is no real part of the zeros. So that is only possible if the S part, that is coefficient of S in the numerator is 0, otherwise there will be no real part. Now what will happen if the real part remains, if due to signal subtraction it is not complete, what will happen, you will find that it will remain. So this will be shifted a little bit on this side, so that will create the problem. So the pole 0 location will not be same, not exactly what is desired, and also by that the exact notch functions may not be achieved. That is the only drawback. But nowadays, as you know, the signal conditioning, the component tolerances are less and less going to be, so that it is very easy to get the whatever the desired value of the, or whatever the designed value of the resistance or capacitance, that we can achieve very easily. So with this we come to the end of the. So you see that's how this signal comes, so that I can staircase waveforms. Okay. So with this I come to the end of the lesson 23 of industrial instrumentation. Welcome to the lesson 24 of industrial instrumentation. In these lessons we will consider piezoelectric sensors. Now as you know, piezoelectric sensors is based on piezoelectric crystals, right. So it has a property that if you apply a force across the surface of these piezoelectric crystals, I will get a voltage, and this process is reversible. That means if I apply the voltage, I will get the force also. So utilizing these principles, obviously I can make the sensors which can measure force, and piezoelectric crystals is extensively used for as I told you, that is reversible. That means it is extensively used for generations of the ultrasonic waves. As you know, there are ultrasonic sensors ultrasonic sensors are used extensively in the case of flow measurements and all these things, like ultrasonic flow meters are there. So you have seen that actually there we are using the to launch the ultrasonic signals. We want that ultrasonics, I mean piezoelectric sensor, piezoelectric crystals actually we have used there. So it is another use, and also the piezoelectric crystals, as you know, it is used for measurements of for the generations of the very stabilized frequency, because piezoelectric crystal, if you will see later on that it has a if you draw the equivalent circuit, that you will find that it has a very high selectivity. It helps to make the oscillator which is very stable in frequency. These are the all different applications of the piezoelectric sensors. So we will discuss one by one what are the and piezoelectric crystals. We will find that I need a special type of amplifier to those to amplify the charge generated across the plates of the piezoelectric crystals. Okay. The equivalent circuit is like this one. You see, I have a inductance. Let us look at. I have an inductance L. Then I have an inductance L, I have a resistance R, C, and also a parallel capacitance C dash. This value of L is very, very high in the case of piezoelectric crystals. That makes the frequency stability excellent. Otherwise, nobody should care for these quartz crystals, right? In this lesson, we will see that at the first part of the lessons, we have discussed the basically the piezoelectric sensors, which is used for the measurements of the displacements, accelerations, which can be used as ultrasonic generations of the frequencies or ultrasonic waves, and also it can be used in the crystal oscillator. And the second parts we have discussed a very important pneumatic system, which is called the flapper nozzle systems with the feedback systems, right? And it's very fail-safe devices. As you can, if you compare with electrical devices, it never fails actually, this flapper, except the routine maintenance of the orifice, because entire operation depends on the orifice width also. So diameter of the orifice is also very important. It should, after over the long use, it should not widen, so that you have to change, you have to make the change in entire calibration. Otherwise, it is a just fail-safe devices. It never happens that it is not working or it fails. So that is a great advantage of this type of pneumatic system. For this reason, it is used over the years in the industry, and still it is used in some of the industries like hydrocarbon industries, where high voltage is restricted. That means I cannot use a voltage or any devices which has a voltage more than 40 volt, because you know there is a large, if you have a large actuator or large valve control valve, I need the voltage at least of 220 volt. To create a large torque. That is not possible, because that voltage is not allowed in the hydrocarbon industry. Though the transmitters are electrical, that's fine, but the basic actuator, basic sensors there are the basic pneumatic, because it is totally hazardous free, right? Because only supply we have instead of electrical supply, so we have a pneumatic supply there, right? So with this, I come to the end of the lesson 24.